What if you could predict tomorrow's weather just by knowing today's weather conditions and a list of historical probabilities? That simple idea powers one of the most useful tools in math and data science, the Markov chain. Today, I'm going to break down Markov chains in the simplest way possible using only linear algebra and a realistic 5-state weather model. By the end of this video, you'll see exactly how a single translation matrix and a few vector multiplications can forecast the weather days ahead, and even reveal the long-term average conditions for a given region. Let's get started. Well, to begin, what exactly is a Markov chain? A Markov chain is a mathematical system where the next state of a given thing depends only on the current state. We call this the memoryless property, which is a major component of Markov chains. In weather terms, this can be described as a chance of rain tomorrow depending only on whether it's sunny or stormy today and not what happened on, say, last Tuesday. We can model Markov chains with two simple linear algebra tools, a translation matrix and probability vectors. The translation matrix tells us the probabilities of moving from one weather type today to another tomorrow. This matrix is a 5x5 grid that shows every possible way that the weather can change from today to tomorrow. Each column represents today's weather and each row represents tomorrow's weather. The numbers inside are probabilities, as decimals are percentages, and every column adds up to exactly 1 or 100%. The probability vector is just a column of 5 numbers that always adds up to 100%, showing today's weather chances. This is a simple column with 5 numbers that always add up to 1 or 100% and tells us the current weather situation as probabilities. Now, for our example of how to use Markov chains in basic weather terms, I have created a simple 5-state weather model to use for this example. Although this model will simply explain how Markov chains can work, it is much simpler than true deterministic weather models to use to forecast, such as the GFS. Here is our 5-state weather model. The states, in order, are sunny, cloudy, rainy, thunderstorm, and tornado. As for the probabilities, I have made up a few probabilities that seem to be realistic for the matrix. Each probability in transition matrix P is as following. If today is sunny, then tomorrow has a 70% chance of being sunny, an 18% chance of being cloudy, a 7% chance of being rainy, a 4% chance of a thunderstorm, and a 1% chance of a tornado. If today is cloudy, then tomorrow has a 45% chance of sunny, 30% chance of cloudy, 15% chance of rainy, 8% chance of a thunderstorm, and a 2% chance of a tornado. If today's rainy, then tomorrow has a 35% chance of sunny, 28% chance of cloudy, 22% chance of rainy, 13% chance of a thunderstorm, and a 2% tornado chance. If today is a thunderstorm, then tomorrow has a 30% chance of sunny, 22% chance of cloudy, 23% chance of rainy, 22% chance of a thunderstorm, and a 3% tornado risk. Now, if today's a tornado, then tomorrow has a 60% chance of being sunny, 18% chance of being cloudy, 12% chance of being rainy, 8% chance of a thunderstorm, and a 2% tornado risk as well. Now, how do we actually predict tomorrow's weather? We simply use matrix vector multiplication. General matrix multiplication is done as the following. For this example, we will use matrix A and a vector V. First, take your matrix and multiply each column of the matrix by each row of your vector. Then, once you have done that, add each column together to get the final vector product. Now, back to our other example. So, if today has a 100% chance of being sunny, you take this vector with the 1 in the first row multiplied by the matrix. In doing this, you will get that tomorrow has the probabilities of 70% chance of sunny, 18% chance of cloudy, 7% chance of rainy, 4% chance of a thunderstorm, and a 1% tornado risk, which is the vector for probabilities after a sunny day we mentioned before. Now, let's say today's weather is not 100% probability, and there's a 20% chance of today being sunny, a 30% chance of today being cloudy, 25% chance of rain, 20% chance of a thunderstorm, and a 5% tornado risk. To find tomorrow's probabilities, we simply multiply the entire translation matrix P by this vector. So now, to calculate, take each column of the matrix P times each row of the new vector. 0.2 times column 1, 0.3 times column 2, and so on until you have multiplied each column of the matrix by each row of the vector. So, after one day, the mixed stormy weather has shifted to a roughly 45.25% chance of sunny, 24.9% chance of cloudy, 16.6% chance of rain, 11.25% chance of thunderstorm, and just a 2% chance of a tornado. When adding this all up, it successfully adds up to 100%. For the day after tomorrow, you simply take this new vector and multiply by p again. That's called p squared times the original vector. Keep doing this, and you get p to the third, p to the fourth, and so on. The beauty in this method is that you never need to remember yesterday's probabilities, and you can just use today's vector and one matrix multiplication to forecast tomorrow. Additionally, if we keep multiplying for several days, the probabilities will begin to stabilize. Then, after many weeks or months, no matter where you started, the weather probabilities will begin to settle into a fixed, long-term distribution. For our model, after calculating a significant number of percentages in a row, the long-term averages level out at approximately sunny with 57.3% of days, cloudy with 22.1% of days, rainy with 11.8% of days, thunderstorms with 7.3% of days, and finally tornado with 1.5% of days. That means in this specific region, you'd expect sunny weather more than half of the time, cloudy days quite often, thunderstorms on about 7% of days, and tornadoes staying rare at roughly 5 to 6 days per year on average. This was all done with linear algebra, where each state becomes a vector in a probability space, and one day forward is a single matrix multiplication. Furthermore, Markov chains aren't just for weather. The same concept controls Google's search engine, models stock prices, predicts DNA sequences, and helps AI make decisions. Anywhere you have states and probabilities that depend on only the current state, Markov chains can give you a simple yet powerful tool. In conclusion, Markov chains are a vital tool for mathematicians, statisticians, and even meteorologists in a wide variety of fields. Anyways, as always, thanks for watching, and don't forget to like and subscribe. I'll see you in the next one.